The topic for this video is trigonometric substitution, sometimes called inverse trigonometric substitution, but most commonly called trig sub. So we started looking at area under a curve by drawing the curve and recognizing some geometric shapes that its graph made, right? Shapes like triangles, rectangles, trapezoids, and circles. We then used the formula for the area of these shapes to evaluate the area under the curve, or the definite integral. For example, if we look at this integral here, the integral from 0 to a of the root of a squared minus x squared, we would have recognized this as the area under this graph from x equals 0 to x equals a. And we would have recognized this function here as the top half of the circle, x squared plus y squared is equal to a squared. The top half, because the bottom half of the circle would have been the negative root, right? That would have been the negative root of a squared minus x squared. So this curve is the top half, but the integral is not evaluating the entire half because it's going from 0 to a. So if it goes from 0 to a, then we are looking at 1/4. We are looking at 1/4 of that circle. And since we know that the area of a circle is pi r squared, if our radius is a, then the area under this curve, which is the definite integral from 0 to a of the root of a squared minus x squared, we would have said by geometry that it is equal to 1/4 pi a squared. In this lesson, what we're going to do is learn how to evaluate integrals like this using antiderivatives and the fundamental theorem of calculus. So the first thing that we're going to do is begin with a strange change of variables, or a substitution, a bizarre substitution. And that substitution is this one. We're going to let x be a sine theta. And then if you calculate, well, dx is a cos theta d theta. And the thing, we want to notice a couple things about this. So I'm going to make a couple remarks about this substitution before we go any further. And the first thing is the name trigonometric substitution comes from the fact that we are introducing a trigonometric function here, right? There are no trig functions in that integral. We are making a change of variable, which is going to introduce a trig function. Something else to notice is that this kind of change of variable is opposite to the typical u substitution. Opposite how? Well, in a u substitution, the new variable, which is u, is expressed as a function of the old variable x. In this substitution up here, x is a sine theta, the old variable x is written as a function of the new variable theta. So that's backwards. If we wrote theta in terms of x, if we wrote the new in terms of the old, we would get theta is the arcsine of x over a. Because the arcsine is an inverse function, this technique is sometimes called inverse trigonometric substitution. And lastly, since the range of the arcsine is from minus pi over 2 to pi over 2, this substitution is only valid for thetas in that interval. So from minus pi over 2 is less than or equal to theta is less than or equal to pi over 2. So after all of those remarks, you probably still have another question, which is why? Why would we do this? And so we're going to take this integral and work through the calculations and figure out how making an introduction of a trigonometric substitution of a trigonometric function unlocks the integral for us and lets us evaluate it as a trigonometric integral. So let's scroll down here and we'll see the original integral and the original substitution that I just recopied here. And since we're making a change of variable, we also have to change the bounds. We have to change the bounds as well. So when x is equal to 0, theta is the arcsine of x over a. So it's the arcsine of 0, which is 0. So we get theta equals 0. When x is a, theta is still the arcsine of x over a, which is the arcsine of 1, which gives me pi over 2. So from 0 to pi over 2 in terms of theta. And then we replace everything like we normally would in a substitution. So the dx gets replaced by a cos theta d theta. A stays in place. X is a sine theta, everything is squared, so a squared sine squared theta. Then we're just going to run through a little algebra here, but now notice that this is just a trigonometric integral. So we're going to factor out an a squared, and what do we notice? 1 minus sine squared pops out. 1 minus sine squared, so that is everybody's favorite trig integral, so cos squared plus sine squared is equal to 1. So 1 minus sine squared theta is cos squared theta. So 1 minus sine squared gets replaced by cos squared theta. Everything else just gets recopied. And then we notice we have the square root of squares. We have the square root of squares. And so hopefully in your calculus course or some previous algebra course, it was drilled into you that the square root of x squared is the absolute value of x, not just x. So when the square root and those squares cancel, well, they don't cancel perfectly, we get absolute value of a cos theta. That is not what we want. That absolute value is in our way, so we have to work to get rid of it. So the first thing we can notice is that if a is the radius, then a is a positive value. So the absolute value of a is just a. And next, the restrictions on theta come in super useful here, because if theta is between minus pi over 2 and pi over 2, then we get this part of the cosine graph. And in particular, that part of the cosine graph is positive. So because of these reasons, we can let go of the absolute value and multiply those two terms together. The a's multiply to a constant a squared, which I will pull out, and then cos times cos gives me cos squared, which now is one of the very first integrals that we looked at when we did trigonometric integrals in the previous unit. Cos squared, we used a half angle identity. Cos squared can be replaced by 1 plus cos of 2 theta over 2. The 1/2 I will pull out in front, so I get 1/2 a squared. Antiderivative here, antiderivative of 1, theta, mini sub here. So a substitution that I will not write down. Antiderivative of cos is sine. 2 theta remains, and I get a 1/2 in front. There's my derivative, antiderivative, that I want to evaluate from the top to the bottom. So the 1/2 a squared stays out. Theta is pi over 2 minus 1/2 sine of, well, 2 times pi over 2 is pi, minus 0 and 0. Sine of pi is also 0, and so that leaves us with just the pi over 2. Multiply that by 1/2 a squared, and we get 1/4 pi a squared, which was exactly the same value that we got when we did the argument by geometry.